All right, if you need me, I'll be in the office.
Hi, I guess I just should start talking? I don't know how this works. Hi, my name's Kim. I thank you for welcoming me to your seminar. I should probably start by saying that the research I'm going to talk about here is not my main research focus. So my work looks primarily at memory consolidation, primarily consolidation processes that happen during sleep and in conditions of sleep deprivation. But this is some work that I've been doing for a number of years with a collaborator, Susan Wagner-Cook, who's at the University of Iowa. So she's really the expert on this work. And I say that now because if you have some questions, I may not necessarily be able to answer them all. All right, so to start off, this work is going to look at how hand gesture affects mathematical learning. And I want to start by talking just a little bit about what gesture is and how it works with speech. So as you've probably realized at this point in your lives, speech and gesture form a really nice unified integrated system. So the great thing about it is gestures can communicate information, sometimes information that's present in the speech, sometimes additional information, and it's time locked to the speech. So speech and gesture are really coordinated at the level of the millisecond, right? So it's really well coordinated system. So I just want to talk to you a little bit about different types of gestures that people use all the time. So the first type of gesture that you've probably noticed a lot if you've been following the presidential campaign at all are beat gestures. So I think Obama is probably the best demonstration of this. And you see when people are giving speeches, they'll often just kind of like pound their fist in order to emphasize a given word or a given concept. So those are really common. They don't add any additional information, but they do add emphasis to the accompanying speech. The second one are called deictic gestures. Here we just mean simple pointing gestures. So deictic gestures happen very early in development. So pre-verbal infants use them all the time. And of course, people use them throughout adulthood as well. All right, and so the next one is probably the kind of gesture that you think of most when you hear the word gesture. So this is called an iconic gesture. So this is a gesture that represents some information. So the example I'm giving you here, is like an example of cutting scissors. You know, you have got the idea of like a telephone. This gesture, I think, maybe is not as relevant to younger folks, because I think it started when we used to have an actual handset where you would hold an actual phone, which doesn't happen very much anymore. And then the last kind I'm calling representational gestures. So I don't have a good example of this, but you'll see some in the videos I'm going to show you. So representational gesture is going to be a type of gesture that embodies information that may or may not be present in the speech. So it may provide additional information that you can't get from listening to the speech alone. So the types of gestures I'm going to be concentrating on are really going to be the latter here, representational, and a little bit of pointing or deictic gestures. All right, so there's been a lot of work looking at gesture in mathematical learning, primarily in children. So we know that if children observe gesture or use gesture during mathematical learning, it can improve their learning on a number of tasks. This has been shown in conservation tasks, in symmetry tasks, and in mathematical equivalence. So I'm going to focus today, the first part of this talk, on mathematical equivalence. So what we found, or what's been found in the past, is that learning that is accompanied by gesture is more stable across time. What that means is if children produce gestures while they're learning, the learning is more stable and less resistant to interference or decay. So what you're looking at here is data from a study in 2006 by my collaborator. The two dotted lines are when they see speech and gesture, or when they simply gesture during learning. And the straight bar is when they learn with speech alone. So what you see is that this follow-up test, which occurs 1 month after initial training, those individuals who gesture during instruction show essentially no statistically significant loss of learning, whereas those who learn in speech alone show a dramatic drop in learning. All right, so our first study is going to be in children, and we have 3 primary questions. So most of the research on gesture and children has looked at gesture production. So what we want to know is whether or not the mere observation of hand gesture during learning is going to affect performance. All right. Secondly, we want to look at transfer of learning. So in math learning, physics, in most of the STEM fields, we're not just interested if you can perform well on the exact problems I've given you. We want to know if you can transfer your learning. Now, research throughout psychology has shown that transfer effects are really small or modest at best. So we're going to look at a very modest form of transfer here, which I'll explain in a minute. And lastly, we want to know if the effective gesture holds even if it's produced on a classroom-wide level. So importantly, all of the previous studies that have looked at how gesture improves learning has used one-on-one instruction. So as you probably know, one-on-one instruction leads to greater learning anyway. And if gesture is only applicable when you're teaching someone one-on-one, then it's not really going to be very useful in a classroom setting. So we wanted to know whether or not this effect holds on a classroom-wide setting. And if you guys have any questions, please feel free to try. All right, so like I said, our first study is going to focus exclusively on mathematical equivalence. So equivalence is a problem like this, so where you have 9 plus 4 plus 7 equals 9 plus something else. And so in our training and our testing, we're going to use what's called equivalent add-ins, which means that one number is going to be repeated on both sides of the equation. So we know that in this country, children have a really difficult time understanding equivalence. This is not true for all countries, but we're a little bit behind in this. So they have a really difficult time forming the understanding that the equal sign is a relationship, right? Instead, what they typically say is if you ask them to define the equal sign, this is 2nd through 4th grade children, they typically say things like, it means put it all together. It means add everything up. Or they'll even say things like, that's where you put the answer. And one of the reasons is because we train children with examples like this all the time, right? It always goes left to right. You never see something, a problem, right, where the equal sign happens here, so you would never have a blank, equals 8 plus 6. So they don't tend to understand this relationship. And this is a problem because it's been shown that understanding of equivalence and understanding of the equal sign predicts later learning of calculus and later math concepts. All right. So here's what we did. So this is data that was collected here in the Lansing School District. Central Michigan. I'm not supposed to tell you what's done in Lansing. Some random city in central Michigan. We had 184 participants from 2nd, 3rd, and 4th grade. You'll see that the 4th grade, we only have 6 children. That's because these children were from a combined 3rd and 4th grade classroom in one of the schools. We didn't actually look to recruit 4th graders. And we conducted this experiment in the regular classroom. So we had 22 individual classrooms. All right. So our training is very simple. On day 1, we come in and we administer a basic pretest. The pretest has 6 equivalence problems. And the reason we do this is because some children, of course, already have an understanding of equivalence, and so we don't use them in our study. So if they got even one problem correct on the pretest, even if it was, by random chance, we don't use them in our study. So they're then shown 6 videos of an instructor explaining an equivalence problem, and I'll give you an example of that in just a minute. So importantly, the critical notion here, the critical manipulation, is that for half of the children or half of the classrooms, the instructor gestured while she was giving the instruction, and for the other half, she did not gesture. And then after each individual problem, children would solve a similar problem on their own. All right. We then give them a post-test, so again, just 6 equivalence problems with equivalent add-ins. And then that's the end of day 1. So then we return 24 hours later for day 2. So again, we're interested not just in immediate learning, but also stability of learning across time. We use a 24-hour period here to look at immediate effects. So we know a lot about what gesture does on immediate training and 1 month down the road, but we don't really know anything about that in-between period. So we chose 24 hours for this study. All right, so on day 2, they get a second post-test, which are going to be 6 novel equivalence problems. So all the problems are going to be different throughout the experiment. And these 2 will have equivalent add-ins. And then importantly, we have a transfer test. So our transfer test has only 4 problems. Now, those of you who do research with adult humans, you may notice that our tests are very short. And this is because we're dealing with 7 to 9-year-old children. We can't give them a 100-item test. We'll lose them at about number 10. So they have 4 transfer problems. And the transfer is actually different between 2nd and 3rd graders. So the 3rd and 4th graders have the same transfer test, but the 2nd graders have a different one. So the 3rd and 4th grade children are going to have an equivalence problem using multiplication instead of addition. And again, we're going to have equivalent add-ins. So the 3 is going to repeat on either side. When we first started this experiment, we gave this transfer test to our 2nd grade children as well, but it turns out that 2nd graders don't know how to do multiplication. So we had to come up with a different idea there. So here we give them equivalence problems, but this time they don't have equivalent add-ins. Right. So importantly, when you do have equivalent add-ins, obviously you can just drop the 3, and in this case multiply the 5 times 2, in the addition case add them 5 times 2. So here it's in some ways less far transfer, but it's also requiring them to make sure that they do the actual full problem. Okay, so now I want to show you the difference in the training. So what I'm going to show you first is a video that includes gesture, and second, a video that doesn't include gesture. Oh, well, that's kind of a problem. Anyone know anything about technology? Why this might not work?
Unfortunately, no, but I could get some.
Well, let me just try to unplug this and see. Is this connected? If I can just hold this up. Let's see.
So I want to make one side equal to the other side. So 4 plus 6 plus 7 is 17, and 10 plus 7 is 17. So one side is equal to the other side.
All right, so can you guys tell what she's doing in her gestures here and why that might be important? So what she's doing is she's really identifying the different sides of the problem, right? So this is one side, obviously, and this is another side. And what that's supposed to signify is that these two things are separate entities and should be equal. So here's the exact same problem without gesture.
So I want to make one side equal to the other side. So 4 plus 6 plus 7 is 17, and 10 plus 7 is 17. So one side is equal to the other side.
All right, so they're obviously pretty similar, and we worked really hard to match these videos, so we made a whole bunch of videos and then chose the 2 that matched the best. We didn't use the same audio track. That would have been better, but when you can see someone's mouth moving, if it's even a little bit off, it's really distracting. So what you're looking at here are just amplitude plots of the same problem with gesture and without gesture. So we matched for intonation, we matched for eye gaze, we matched for timing as well. So the videos were really well matched. So we don't think that any effects we have really could be explained by the videos. And this is actually important because, as you can imagine, if you were talking and you had to hold your hands steady versus you were allowed to freely gesture, you're actually going to show more amplitude modulation, more prosody in your speech if you're allowed to gesture. All right, so here's what we found. If we look at the first post-test, we already see an effect of gesture. So here you're just looking at proportion correct, and the gray is going to be the speech alone group, and blue is going to be the gesture group. So this is immediately after learning on day 1. Now, if we look at post-test 2, we have something really interesting going on. Now, of course, the gesture group is still outperforming the speech alone group, but what you can see is that the speech alone group is really showing maintenance of learning, but certainly no additional benefit, whereas the gesture group is actually getting significantly better on day 2. So they're actually showing an improvement in learning across the 24-hour period. Now, our transfer test is obviously a little different, so you wouldn't expect exactly the same performance. And we don't see exactly the same performance, but we do again show a benefit of gesture over the speech alone. And so this is, of course, collapsed across the 2nd, 3rd, and 4th graders, so the transfer test is a little bit different between them, and we found that when we separated them, the results essentially look the same. So we collapsed them together, but again, you're seeing this big benefit of gesture over speech alone. Now, importantly, obviously the gesture group is performing better immediately after training. If we take into account performance on post-test 1, we still see a benefit of gesture on the second post-test and the transfer test, suggesting that they're not just doing better immediately, but they're also showing changes across time. All right, so again, significant effect of gesture in each test. And our follow-up tests, our day 2 results, remain reliable even after we take into account the improved performance on that initial post-test. All right, so what we can say from this study as well as others is that we know that gestures can help to improve learning even when it's presented at a classroom-wide level. And we know that gesture improves learning even only during gesture observation, even without gesture production. We can also say that gesture helps to improve transfer to novel problems. And importantly, at least in my case, that the effective gesture seems to increase with time. And I'm going to show you some work in adults that also shows this. So this is really interesting to us. But again, like I said, most, if not actually all of the work on gesture and learning focuses on children, really specifically in a single age range, pre-adolescent children. So what we wanted to next look at was whether or not gesture will improve mathematical learning in adults. Now this is a somewhat difficult question to answer, of course, because by the time children come to college, they know a lot about math. So we have to teach them something absolutely new that prior knowledge isn't going to have a huge effect on. So let me tell you first why I think this could have an effect. So there isn't any work on gesture and math learning in adults, but there is work on gesture and learning in adults. So if we look at basic memory processing and basic memory tasks, we know that if new information is presented with gesture, adults are more likely to remember it, they're more likely to recall this information later. And we know that they're more likely to acquire foreign language vocabulary if the vocabulary words are presented with gesture, even if they also get the information in speech. So even though the gesture is redundant with the speech and redundant with what they're learning, it still improves vocabulary learning in adults. All right, so again, our main question here is just whether or not gesture is going to affect mathematical learning in adults. All right, so the way that we do this is by using an abstract symbol system. So this is based on some work that Vladimir Slutsky and Kaminsky have done. So I'll get to the task in just a minute, but first I'm going to give you just the layout. So the layout of the study is going to be very similar to the last one. So first we're going to give them a familiarization phase, which means that we're just going to teach them the rules of the abstract symbol system. Again, I'll get to that in just a minute. And then we're going to provide them instruction. So an instruction, just like with the children, they're going to watch 6 videos of an instructor explaining how to solve problems in the symbol system. Again, for half the participants, the video is going to include gesture with the instruction. For the other half, it's not going to include gesture with the instruction. All right. In the first post-test, they're just going to solve 24 problems in the same system. And then they leave for the day, return 24 hours later. They get a transfer test, which again is going to be slightly different than their trained system. So you're going to, again, answer 24 problems in an isomorphic symbol system. I'll get to that in 1 second. And then a second post-test. Okay. So here again, we're looking at immediate effects of gesture on learning, as well as whether or not gesture changes their representation with time, and whether or not it can affect transferred learning. All right, so this is our symbol system. So our symbol system is composed of 3 symbols, and these are the exact instructions that are given to participants. So they learn each of these rules one at a time. They're pretty basic. So again, we have 3 symbols. We call them circle, diamond, and this one's called squiggle, which kind of always makes me want to laugh a little bit. And these are the basic symbols. So after each rule, they're given one question about that rule. And what we used to do when we first started this training is we would let them continue on to the training regardless of how they answer the questions about the rules. But that led to a lot of problems because these are our participants are primarily Psych 101 students who don't really care about our symbol system and don't really like math. So we found a lot of people just would go through the program. So what we did is we started to treat our undergrads like rats. So we borrowed some tools from the behavioral neuroscience literature, and so now if they get a question wrong, we give them a 10-second timeout so so they can't continue the experiment for 10 seconds. So they are learning the rules, and then they have to redo that question. All right. So this is never shown to the participants, but this is just a schematic to explain to you what this system looks like. So again, diamond and circle, if you combine either one of them together, you get the other thing. Squiggle is our operator, so squiggle combined with anything else is going to be that thing. And then diamond and circle combine to make squiggle. Okay. So again, they're not shown this, so it's a lot more difficult to learn. I just wanted to give you guys an idea. All right, so let me show you the training. The problem is going to be exactly the same for the gesture. No gesture condition. Here I'm going to show you the gesture first. A couple of things to note. In the last study, we're trying to use more representational gestures. Here we're using simple pointing gestures. So I'll let you watch it. And so this is my collaborator. It seems a little funny that she's kind of in this weird silhouette. She was actually pregnant at the time, and we didn't want that to show because we thought it might add some weird artifacts.
So diamond combined with diamond makes circle, and circle combined with circle makes diamond. So one side reduces to make diamond. I already have a circle on the other side, so what combines with circle to make diamond? The answer is circle.
Can you guys hear that okay? All right, so, just weird. So now this is the video without gesture. Again, exactly the same thing.
So diamond combined with diamond makes circle, and circle combined with circle makes diamond. So one side reduces to make diamond. I already have a circle on the other side, so what combines with circle to make diamond? The answer is circle.
All right, so again, you can see the speech is well matched. This video is playing a little slow, so it wasn't really aligned with her actual mouth movements. But of course, in the real study, it didn't look like that. All right, so now we have our test. So in our test, we had a number of different types of problems. So first, we had really simple problems where if you understand the basic rules of the system, they should get these right. Okay, so now that you guys have learned so much about the system, what's the correct answer here? So diamond plus squiggle is what? Yeah, it's an easy one, right? Okay, how about this one? So circle plus squiggle is circle plus what? So the answer here is going to be diamond, so here that's going to be circle. Okay, and then we have, so that one's obviously a little bit more difficult, and then we have ones like this. Which actually, if you just go through it, it just keeps reducing down. I don't remember what the actual answer is, but it's actually not that hard. All right, so then for our transfer test, and again, this is based on prior literature, what we do is we give them essentially the exact same system, but there are new symbols, right? So here we've got this little vase and a little ring and a ladybug. And what you can see is that which one is it now? Oh yeah, the ring is going to be the operator, so ring plus anything is going to be the other thing. And you can go through them and they all match up. Now importantly, during our transfer test, they had this information up on the screen the entire time. Because of that, I'm not sure why people didn't more often get 100%, but they didn't. And then of course we just gave them the same basic questions. And again, it should be really easy. If you took 5 minutes to look at this, you'd be able to answer these without a problem. All right, so now we're gonna look at our results. So again, just to remind you, in the children, what we found is that gesture improved immediate learning, it increased learning with time, and it showed better transfer to the new system. All right, so if we look immediately, again, here's performance in the first post-test, which is going to be that immediate post-test right after training, and we see already a benefit of gesture in the green over speech alone in the gray. 24 hours later, post-test 2, we again see the exact same pattern we saw in the children. The speech alone group seems to be maintaining their performance, whereas the gesture group is actually increasing their performance across time. And then finally in the transfer test, again, just like the children, we see that the gesture group is doing better on transfer than the speech alone group. And here again, performance is actually all not very good considering they have the symbol system right in front of them. But these are MSU undergrads. All right, so taken together, what we can say is that gesture seems to have immediate effects on learning. It seems to have a benefit for consolidation across time, and it seems to increase transfer to novel problems. And again, importantly, we're showing this with the mere observation of gesture, not with gesture production. So what we can say, what we think, is that gesture is doing more than just facilitate learning, facilitate communication in the moment. So one of the criticism of the gesture work is that gesture simply increases comprehension, and that's true. There's been a number of studies to show this. If you watch someone speak, and you watch someone speak with gesture, you'll understand the speech better if gesture accompanies the speech. And importantly to us too, gesture seems to affect the nature of the representation across time, at least across a 24-hour period. So the big question though is why? What is the mechanism underlying this effect? So why does gesture help? What's important about it? What's unique? What's good? Does anyone want to take a guess?
Kind of breaks the whole thing down. So it's like you're only looking at where they're gesturing and it's like smaller parts instead of looking at the whole equation in the first part.
It's really interesting. Good. Did you have another?
I was thinking of multiple inputs that are coordinated. So like when she's talking and gesturing, there's the pointing at what she's looking at, as so there's this visual input as well as the auditory.
Right, yeah, so multimodal input always shows better learning. Good. I'm not actually going to answer this question. I'm just going to try to give you a little piece of it. All right, so there's a lot of potential mechanisms. The first one I think that always comes up is directing attention. So the one thing that we know for sure is that gesture helps to direct your attention in some way, right? Whereas if you don't have the gesture, your attention could be diverted anywhere. How many could be diverted anywhere anyways? So if you think about that, and if you think about a typical classroom, right? If you're teaching, as I do, Psych 101 with 500 students, you can't point at the screen because it's 15 feet above you. So what do people typically use in classrooms that could also direct attention? Right, exactly, which doesn't work on the screen, interestingly. So you would assume then if gesture isn't something special, if it's not doing something unique, then a laser pointer would have the same effect. So we don't think that simple attention direction is the key, and it's based on this preliminary study we have. So what you're looking at is the exact same task I just showed you. 3 conditions now. We have a regular gesture condition, a regular speech alone condition, and a condition that has the exact same, essentially, attention manipulation, but using a laser pointer instead of a hand. Now here, what we can say is, I'm not sure that the laser pointing is actually impeding learning, even though obviously that bar is a little bit lower, but it's certainly not improving learning, right? So if all gesture is doing is simply directing attention to the right spot, the laser pointer should do the same thing. All right. So there are a couple of other potential mechanisms. So one thing they could be doing is it could be providing some sort of motoric representation. So there's a lot of work in the embodied cognition literature and some other literature to suggest that if you perform an action yourself, you're going to remember that better. So if I gave you a list of verbs to remember, or I asked you to act out the verbs, and people do these studies, you're going to remember those words better if you actually act out the verb, right? So if I tell you to swing a tennis racket, or you just have to read the word swing a tennis racket, you're going to remember it a lot better if you actually make the motion. Another thing that we think might be happening is that it's creating a more proceduralized representation of the information. So across hundreds of years of research on memory, We know that a declarative memory representation is more prone to decay, is more prone to interference than a proceduralized representation. So this is actually known by just about everyone. We have the old adage, it's like riding a bike, and you know that if you rode a bike all through grade school and didn't pick it up again until you're 30 years old, you can still get on your bike and ride it without any problem. So we know that proceduralized representations or proceduralized memories are really rich and really resistant to interference or decay. And it may be something totally different. So we're just starting to look at this. We're starting to piece together the reasons and the mechanisms underlying these effects. We have a number of studies that we're working on. Today I'm just going to give you a tiny bit of information on a study using eye tracking. All right, so in our replication, we're going to do exactly the same experiment we did with the adults here at MSU, but they're going to wear an eye tracker throughout the entire experiment. Okay. And in case you're not familiar with eye tracking, it's really basic. What we can do is after the study, after we process the data, we can look exactly where a person looked in a given scene. So I'll give you a better example of this. So for example, this is a visual search task. This is a little child trying to find the one fish that doesn't match up with the other fishes. Obviously it's right here. And so what we can do with the eye tracker is we'll know exactly where the person first starts looking, right? So in this case, she first starts looking up here. And then we can track exactly what her path was throughout the search, right? And so there you can see she kind of looked over here, came down, fixated on here, went back up and came back down and settled on her decision and then made her choice. That's the orange fish. All right. So in our adults, again, same exact design. They come in on day one. They do the whole training. They get the first post-test. They return 24 hours later for a second post-test and a transfer test. Now, they have the eye tracker on the entire time. Of course, what we're most interested in is where their eyes are during training. All right, so the results are slightly different from our results here. You see, of course, the benefit of gesture in all three tests, but you don't see the boost in performance after 24 hours. We're not sure why that is. Could have something to do with the fact that they're wearing this giant head-mounted eye tracker. Could have something to do with the fact that they're University of Iowa students instead of MSU students. I don't know. But other than that, the results are pretty similar. All right, so now the important thing, and I think the really interesting thing, is what these people are doing while they're watching the video. So I'm going to show you one video where the person does receive gesture, another video where they don't, and then I'm going to let you watch them both together. So let me explain to you what you're looking at. So these red crosshairs are going to be her or his fixation points. Right. And the one thing I want you to notice about this, there's no sound to these videos because it's a video taken from the eye tracker itself. But you can kind of see when her lips start moving. And this one is really easy because obviously she gestures when she says anything. What you'll notice is that for the very first part, while she's talking about how to combine these together, the person's eyes stay fixated on this first part of the problem. And it's not until much later that the eyes fixate over to the other side of the problem. So I'll play it a couple of times so you can get an idea. Oh, whoops. All right, so you can see the person staying fixated on this side of the problem. There's a quick fixation over, but back over to the first side, and then stays over there, and then kind of goes back over here. And now if you remember, in her speech, what she's saying is, of course, what combines with circle to make diamond, I think is what it is. So I'll let you watch that one more time. All right, so now this is a little more difficult to follow, but you can kind of tell when she starts talking because her mouth starts moving. So now here you're going to see a really different pattern. Now the first thing you're going to notice is that the eye movements are a lot jumpier than the first one. So, and this is more representative, I think, or more typical for an eye tracking study. So Obviously, your world is very stable. You've got lots of things in your brain that are helping to keep it very stable, but your eyes move around a lot. And this is going to be, I think, what we more likely see or more often see in eye tracking studies. So one thing you do want to notice, though, is that you can see your mouth moving, so you know she's talking about this part of the problem. And what happens is the person is going to look and watch her face a lot more than she looks at the actual items. And you'll also see that she's going to fixate over here to the other side of the problem a lot earlier than the other person did. So it's about 5 seconds earlier. Okay, so her mouth's moving, so she's talking about that first part. You can see that she's focusing on the mouth as opposed to the problem. And it's really darting all kind of like back and forth a lot more than the other one. So we'll play it one more time. All right, so now I have these pretty well time locked. That's not perfect, but you can get a good idea by just watching them together, because again, you'll see this one either hovering over here or fixating kind of across the problem a lot more than the first one. One more time so you can see the differences there. All right, so we think sort of exactly what you predicted before is we think what gesture is doing is keeping people in the right place. Right? So particularly when we're learning anything new, a lot of times we jump ahead, right? This is basic top-down processing. You do it for everything, right? As you're sitting here listening to me, you're already predicting what I'm going to say next. Even if you don't realize you're doing it. So we're thinking ahead. When you read, you don't read each individual letter, each individual word even. You bounce around. If you read each individual letter, you wouldn't have made it this far in school. So we think that what gesture is doing is in these more complex tasks, it's keeping people in the right spot in the problem, right? So the gesture person is focusing more on this side of the problem, whereas the no gesture one is like flipping to the other end, and the gesture person is of course focusing more on the individual items. Now unfortunately I don't have any more concrete data to show you. I can't process this data on my own. This is all collected in Iowa, and this is all they gave me when I emailed them 2 days ago to force them to give me some data. So I'm sorry I don't have more concrete results for you. All right, but just to wrap up everything I've told you, what we can say is that the mere observation of gesture can improve mathematical learning. And we have at least some preliminary evidence that learning with gesture helps the representation to improve with time. And what we think is going on is that gesture during instruction is interacting with consolidation processes. Potentially because it is a multimodal representation, potentially because it has a more motoric representation, and potentially because it is a proceduralized representation. We don't know why. We're working on that now. And again, the exact mechanism is really not known. What we think, again, from our preliminary analysis of this eye tracking data, is that gesture is helping people keep, in the right spot in the problem. But that may not be all it's doing, and that might not be even why it's having an effect, right? Again, we know from a wide literature that multimodal representations are more likely to be stable. We know that motoric representations and proceduralized representations are going to have, again, a stronger representation in the brain. So that could be a big part of the reason why. Another thing that gesture may do is simply provide additional information or cues to the problem structure, right? To help people understand the underlying structure of the problem. Right. So that's all I want to say to you. I just want to thank my collaborator, Susan Wagner-Cook at University of Iowa, Ryan Duffy, who was an undergraduate in my lab, in my very large and very wonderful lab. That's it. Yes, Devin.
Why do you have eye tracking data for laser pointers, and why it seems like the eyes should track in the same way, but then your data suggests that they're not learning the same way, so why is that?
That's a great question. Well, I would like to tell you that there's a number of reasons why. I would like to tell you that it's because gesture provides an embodied representation, potentially tapping into the mirror system, potentially providing this proceduralized representation that a single dot on the screen is not going to do. I don't have that data, so I don't know. I think you're right. I think that the laser pointer is going to direct attention in the same way, which is why I think it's not simply that your eyes are in the right spot. I think gesture is doing more. I just can't give you any evidence for that yet.
Do you also have any sense for if you can do damage with bad gesturing? Like some people find gestures really distracting.
Yeah, so there's actually some evidence that mismatched gesture, which is a gesture that doesn't match exactly what you're saying, actually shows additional benefits. So it's really hard. These terms are so hard to understand because you can't imagine how a gesture doesn't match what you're saying. But if the gesture represents information that's correct, so if the gesture is correct in some way, but doesn't match what you're saying, it's better than having no gesture at all. Now that being said, if you have some crazy person who's constantly moving their hands in a really erratic way, I don't think that would help. So we've been trying to find a way to have non-meaningful gestures, and when we try to run, like try to create the videos, it's really hard. So we formulated this way of making completely random gestures that matched up, right? So you can imagine, there's a let's go back a couple. Right, so you see this problem, right? And she's obviously pointing. So we can have them do random points, but when you're watching it, it's just horrible. Like it's like you can't watch it because it's so wrong, and it would just never occur. So my guess is that would be incredibly distracting. Yes, but we haven't actually run the study because like just editing the videos is painful, and we're like, we can't make people do this, and it's unrealistic, right? No one is going to be like, diamond and diamond is right. No one's going to do that. So I can imagine that if you had audio taped or audio dubbed something incorrectly, right, that's going to be a problem. But in a naturalistic sense, completely random gestures or completely unmatched gestures don't ever happen. Yeah.
In the video that showed eye tracking without gesture, the eye kept going back and looking at the speaker's mouth.
Yep.
If you were to do something with, say, a narrator, a voiceover narrator and a non-speaking instructor who is simply providing gestures that are timed with what's being spoken,
Yep.
Do you think you would see that same effect where the eye continues to go back to her face? Or would it follow, if you remove the gestures but then still have the presenter standing there inside, will the eye track with what the narration is instructed?
I think what would actually happen is that they would show more fixations across to the other side because they think ahead. Now this is the first eye tracking gesture learning study that's been done, but I have a collaborator who's done a similar study, but instead of seeing the person kind of sideways, the person is standing in front of the problem like this, so you can't see the mouth movements. And we don't, of course, have eye tracking data, but I can tell you the gestures still show a big boost in performance. So you're right, because in that particular example, the person is clearly watching her mouth way more than the person's looking at the problem, which is a problem, which is an issue. But I think and of course these are only two subjects, and some of the other ones what we see is that they're not so much fixating the mouth, but they focus back and forth on the two sides of the problem way more than the gesture people do. Any other questions?
So I was curious about the use of the different symbol system, and I was wondering if you had considered perhaps doing a study with students at the college level who struggle with mathematics in general, and how that, some of those equality problems, I'm wondering if those might produce similar results in that way.
Yeah, that is such a great question. So we're actually working with someone at the University of Cincinnati to study college students with learning disabilities for that exact reason. And in our early discussions, our collaborator started doing some just real kind of anecdotal stuff with his students. And again, anecdotally said that he saw big improvements. But yeah, we need to do that. There is other work in children showing that children who have ADHD show a greater benefit from gesture than children who do not have ADHD. So I do think that it, particularly, I think anyone with any kind of like verbal impairment or language impairment is going to show a much bigger benefit. We don't have access to those people right now here, but like I said, we're trying to do it at Cincinnati. Yeah, no, it's a great question. That's kind of where we want to go. These special populations who are showing who show huge deficits, particularly in math learning and then these more abstract concepts. I think they're the ones who are going to show the biggest benefit from this kind of representation. All right, well, thanks for coming.